This video is to go over the Hardy-Weinberg problem sheet that I gave you guys, and just to kind of demonstrate how to work these problems if you're still struggling with this or if you just need a review. So I'm just going to work through these problems slowly. So for questions 1 and 2, in a given population of 200 humans in a remote Pacific island, 48 individuals have the phenotype attached earlobes, a recessive genetic trait. And so answer the following questions based on that. What percentage of the population are homozygous dominant? Well, we have to know a few things concerning the Hardy-Weinberg equation first. So let me put them here. First of all, we know that P plus Q equals 1, whereas P equals the percent of dominant alleles in a population, and Q equals the percent of recessive alleles in a population. All right. And the other equation is P squared plus 2PQ plus Q squared equals 1, whereas P squared equals the percentage of homozygous dominant individuals, 2PQ equals the percentage of heterozygous individuals, and Q squared equals the percentage of homozygous recessive individuals. Now, these two equations need one another in that if you know P, if you know the percentage of dominant alleles in the population, you can solve P squared, which is the homozygous dominant, because obviously that is the same as P times P, and 2PQ and Q squared, and so forth. So we were asked what the percentage of the population is homozygous dominant, so we are looking for P squared in this problem. And so in order to do that, we have to get a few things first. We know that 98 individuals have the phenotype for attached earlobes, a recessive trait. And so 98 individuals have the recessive trait. 98 have this trait, which is 49% of the population. 49% of the population are homozygous recessive. What is homozygous recessive? Q squared. So 40.49 is equal to Q squared. So what is Q equal to? Why do we need to solve for Q? Well, we need to solve for Q because we know that P plus Q equals 1. And if we can solve for Q, we can solve for P. And so Q in this case equals 0.7. And how did I get that? I just took the square root of both of these sides. All right, so if Q equals 0.7, then P equals 0.3. And if P equals 0.3, then P squared equals 0.09, or 9%. What percentage of the population is heterozygous? Well, this is not difficult because we just do 2 times P times Q. Why? Because 2PQ equals the percentage of heterozygous individuals. So we have 2 times 0.3, which is 0.6 times 0.7, and that is 0.42, or 42%. In a given population of wild Mustangs, brown hair is dominant to blonde. Within the population of Mustangs, there are 168 brown-haired Mustangs. Now, a brown-haired Mustang can either have this genotype or this genotype. Well, that doesn't help us to know that P squared plus 2PQ is equal to 168 individuals. That's not, the equation's not really right, but you get what I'm going at there. So it'd be better for us to solve for what we do know, because we also know that there are 32 individuals 200 minus 168 individuals that have the recessive trait. 32 out of 200 is 16.16 or 16%, and that's q squared. So q squared equals 0.16. Where did I get that? Well, if 168 have this or this, then the other 32 have little b, which is the recessive trait. So q squared equals 0.16, so q equals 0.4, p equals 0.6, because 1 minus q is p. So what is the predicted frequency of heterozygous Mustangs? Well, 2 times 0.4 times 0.6 equals 0.48, 48%. What is the predicted frequency of homozygous brown Mustangs? So our homozygous, big B, brown Mustangs, it's p squared, or 0.36. Given population of Vietnamese potbelly pigs, out of 150 pigs, there exist 180 alleles for the recessive trait blue eyes. All right, so a little bit of a curveball here. We're given the number of pigs at 150, but we're also given the number of alleles for the recessive trait. Well, how many total alleles are in the population? You take the number of individuals times 2 to get the number of alleles. So there are 300 alleles in the population. 180 of those alleles are recessive. So the percent of recessive alleles in the population is 180 over 300, or 60%. And so Q is equal to 0.6, therefore P is equal to 0.4. So what is the recessive allele frequency in the population? 0.6. What is the expected, and because that's Q, what is the expected number of pigs with blue eyes in the population? Well, that's Q squared. Q squared is equal to the percentage of pigs, so that's 0.36. Where'd I get that? It's just 0.6 squared. And so that's 36% of these pigs have blue eyes. You multiply that times the total number of pigs, and you get 54. What is the heterozygous frequency within the population here? 0.6 times 0.4 times 2, that is 0.48. Within a given population, 4,000 vampire bats in Africa, the dominant allele frequency for long hairs is 0.2, so we are given P as 0.2, therefore Q is 0.8, because 1 minus P is Q. What is the allele frequency for the recessive allele? 0.8. What is the frequency of heterozygous bats? 0.2 times 0.8 times 2 is 0.32, or 32%. Now let's write these things down on this side so we don't have to go back. P equals 0.2, Q equals 0.8. Homozygous dominant bats. Well, homozygous dominant bats, that's P squared, or 0.04 times 4,000. What is that? 160. Homozygous recessive, that's Q squared, so that's 0.64 times 4,000. What is that? That's 2560. Heterozygous, TPQ, that's 32% times 4,000, that's half of the other, so it's a total of 180. Dominant alleles, well, there are 8,000 alleles. Where did I get that? 4,000 bats times 2, 8,000 alleles times 0.2, that's 1,600, and then the other is 1 minus that, or 4,000 minus that, so that would be, what, 6,400 alleles. And what are the 5 conditions that must exist for a population to be considered in Hardy-Weinberg equilibrium? Let's see if I can do these off the top of my head. There must be a large population, no natural selection, random mating, no gene flow, and no mutations, because all of these represent no change in allele frequency. Hope that was helpful.